Hello everyone. Today we're going to discuss how to do petrophysical multimineral analysis using genetic algorithms, and we will show some applications to unconventional reservoirs. Before we start, let's take a look at the motivation of why we do multimineral analysis. We know that the estimation of quantitative volumes of rock constituents, which are minerals and fluids, is essential for proper evaluation and development of hydrocarbon reservoirs. And we know from experience that multimineral analysis is a tool that can help achieve this objective, in particular in areas of complex lithologies. Also, multimineral analysis can help set error bars on possible reservoir properties. But in some cases, poor assumptions and limited logging tools can make the process difficult to use. This slide summarizes what we want to do when we go from rocks to measurements to models of rocks. So we start with the real rocks, which are made of minerals and fluids. Then we use some logging tools to obtain the well logs. In this presentation, I'm going to use in the red color to indicate the real measurements. Then we use these measurements to ideally go back to the real rocks, but that is an impossible goal because of the limited amount of information that we have. So we settle for a more simple goal, which is doing inverse modeling, typically linear modeling, where we relate the logs, the constituents, and the fractions. And the result is an approximation to the real rock that has approximate volumes, approximate constituents. But we always need to calibrate this result with independent data in order to build confidence in what we are obtaining. And typically this independent data consists of lab measurements, thin sections, mod log, cross plots, etc. So what are the assumptions of the inverse modeling? As I said before, we're going to assume that the log response and the properties are linearly related. This may or may not be true, but it's true in many cases. Another important assumption is that the constituents are known. Typically, the constituents are determined from independent calibration, such as lab measurements, thin sections, mod logs, cross plots, etc. Besides assuming the constituents, we assume that the properties of the constituents is also known. And these properties are typically estimated from tables, lab measurements, or experience. And then in many cases, we have more constituents than the logs that we have to resolve them. So our assumption is that we are solving only for the most important in order to be able to achieve what we think is a unique solution. So here's an example of how the linear modeling works when we have 4 logs, 5 constituents, and a single depth. So for a single depth, we start with a system of equations that relates the constants for the constituents, which we assume don't change in the interval of interest, the fraction of the different constituents, and the log data. We can separate the components of the matrix even more into the mineral part and the fluid part. And also we use what is called the unity constraint that assumes that the sum of the different fractions present in the rock is equal to 1. So in this case, we have 5 equations, 5 unknowns, and then a unique solution for a given set of constants. However, if one of the constants is missing or more, we may end up with up to 25 unknowns depending on how many constants we know or how many constants are missing. Also, if we have many constituents which are more than the logs that we have to resolve for them, we may end up with a severely non-unique problem. And also, if you're missing at least one constant, the problem becomes nonlinear. How do we apply multimineral analysis in practice? So this slide shows the standard inversion for fractions of constituents using multimineral analysis. In this and other slides, we're going to be using this conversion dashed lines for work performed by the petrophysicist and solid lines for work completed by the computer. So the petrophysicists start with the generation of the coefficient matrix. Then the computer solved a linear system of equations for the fractions versus depth. Then the algorithm computes one set of model logs, and the results are inspected by the petrophysicist on the screen of the computer to check whether the fit between the computed logs and the measured logs is acceptable. If the petrophysicist finds the fit acceptable, then he or she exports the fractions and the model logs. However, if the fit is not considered acceptable, then comes the process of a manual adjustment of the constants. And this is typically performed in a trial and error fashion. The petrophysicists adjust the different numbers in the metrics according to different criteria to see if the fitness can be improved. And then that information is introduced again into the solution of the linear system for the fractions versus depth. Then the computer takes over, and then we repeat the whole process of changing the metrics, solving for the constants, and inspecting the results. Once the results are acceptable, they are exported. But the key part of this workflow is the manual adjustment of the metrics by the petrophysicist. The manual adjustment of the metrics works fine if we don't have too much uncertainty on the composition of the rock and the properties of the different constituents of the rock. But let's examine, for instance, what happens in an unconventional shale. What is an unconventional shale? Well, unconventional shales are typically a complex mix of minerals that range from quartz and feldspar, clays of different kinds, and different types of carbonates. We see large variations between different plays, and we see variations in composition even within the same play. But in many instances, we don't have enough log to solve for the different minerals that might be present in the rock. So let's examine the case, for instance, of the Bakken play in a little bit more detail. Here is the mineralogy of the Bakken Formation from XRD measurements. We represent this mineral composition as a form of a histogram that indicates the relative importance of the different constituents. The original problem that we want to solve consists of 14 minerals and 2 fluids, and we typically have between 4 and 5 logs to solve for it. Obviously, not enough information to solve for all this composition. So what we do is that we go back to the histogram and identify the relative importance of the different components. First, we eliminate the components that don't have a significant presence in the rock, in this case, the calcite and anhydrite. We go to the top end of the histogram, and then we keep the most important mineral in this rock, which is the dolomite, because we're going to model that separately. Then, still we have too many minerals, so what we do is that we group the remaining minerals if they have something in common. So we take the clastics and we create a new class or a new rock that still we're going to call quartz, but we know that these quartz come from a mix of real quartz, feldspar, and albite. We do the same thing with the clays, and then we lump all the clays into a single rock that we're going to call clay. Finally, in this particular case, we model the pyrite separately. So in this way, after identifying the important minerals, the minerals that are not too important, and after the mix of some of the remaining minerals, we end up with what is called the premixed problem. We have between 3 and 4 minerals and 2 fluids, and we have between 4 and 5 logs to solve for it. But the question now is, what are the properties of these minerals that we are creating by mixing the original minerals present in the rock? And the problem with this is that these minerals that we are creating are not necessarily found in tables in the literature, or we don't have information about their properties from lab measurements. As I explained in the previous slide, we changed the problem of too many minerals and few logs to a more tractable problem where we combine different minerals to a number that is similar to the number of logs that we have. But now we introduce another problem, that we are creating minerals whose properties are really unknown. We don't find those properties in any table because we are making up these minerals. So the problem of estimating the constants of these constituents becomes now our central problem. The difficulty is that if we want to do that, it cannot be by bringing more log data because we're already using all we have. But we know that we need more equations, we need more logs, so we need some additional information if we want to estimate these constants, these new constants explicitly. So what we do is that we increase the number of equations by solving simultaneously for all depth in the interval of interest. So we bring more depth into the problem in the same well, or we can bring more depth from different wells that sample the same interval. By doing this, the estimation of the constants can be posed as a global nonlinear optimization problem. And the tool that we're going to use to solve this problem is a genetic algorithm. But we have to keep in mind that even after bringing all this information from additional depth in the same well or additional depth from the same formation from different wells, the problem can be still severely underdetermined. So always in this type of problem, the more we know about the fractions and the constants, the better. The more additional information we can bring into the problem to constrain any of the missing information, the better the result that we will obtain. As I said before, we're going to use a genetic algorithm to solve our global nonlinear optimization problem. But before we go into the details of how we do that, I'm going to summarize very quickly here what is a genetic algorithm. A genetic algorithm is a global search heuristic method based on natural selection and recombination. We iterate over groups that we're going to call generations of possible solutions that we're going to call individuals, starting always from a randomized initial iteration. For this type of algorithm, the individuals in the generations are ranked, and we always keep the best individual from one iteration to the next. The better individuals from each generation are randomly paired and combined to form a new generation, and the iterations continue for a number of generations or until what we call a good enough solution or individual is found. It's important here to emphasize that the solution is good enough, good perhaps to make decisions, but we cannot guarantee that this solution is optimal because only a fraction of the solution space is tested. In general, we could say that genetic algorithms are a good optimization option when the problem can be decomposed into what are called building blocks, whose solutions are subparts of the larger optimization problem, or for problems that are combinatory in nature, which is similar to what we will try to do here in the petrophysical optimization. Now that we know or that we have reviewed the generalities of genetic algorithms, let's see how we can apply that specifically to our case. But before that, let's examine the different components of the algorithm for our particular case. First of all, what is an individual? An individual, in our context, is a single matrix of values. And in genetic algorithms, this must be a vector, it must be a string. So here is the matrix, and we transform that into a long vector. How do we rank individuals? Well, what we do is that we compare the measured logs. Remember that we're going to be indicating them in red versus the model curves that are going to be indicated in blue. So we take the vector, we transform that into a matrix, and then from that we model a new set of curves that are going to be compared with the measured curves. The other question is how to combine individuals. And the technique that we're going to use, that is commonly used in genetic algorithms, is called crossover. And with this technique, what we do is that we take parts of the information from, let's say, the best individuals in one generation, and we combine that information to form the children. In this particular example, we take half of the information from each of the parents, and we use that to create the offspring. Finally, randomization of the individuals and occasional mutations are crucial to ensure that good values are available for selection at every time. In a previous slide, I showed the details of the standard multimineral analysis for the estimation of fractions of the different minerals and fluids present in the rock. What I will show in this slide is how this process is modified when we use a genetic algorithm. The first step is the generation of n random matrices of coefficients within given ranges that are specified by the petrophysicist. What follows is the solution of n linear systems of equations for fractions versus depth. And then using the solution of these systems, the algorithm computes n sets of model logs. These logs are then used to compare with the measured log and extract misfits for all depths using each of the input matrices. Then the next step is to ask, is this the final iteration? And if the final iteration hasn't been reached, the next step is the modification of the matrices that were created at the beginning, this time using the rules of the genetic algorithm that were explained before, like mutation, ranking, and crossover. These new matrices are taken again to the beginning of the process, and then we start all over by solving n linear systems of equations with these new matrices, computation of n sets of model logs, and computations of misfits. When the final iteration has been reached, the next step is that the petrophysicists
checks whether these constants are acceptable or not, if they agree with some preconceived notion or if they agree with some independent data. And if they are acceptable, the next step is to export the fractions, the model logs, and the coefficients that has been estimated. If the petrophysicist thinks that this constants needs to be modified, the next step is to adjust them manually for whatever coefficients he or she may think that need to be changed, and the whole process starts again. So we generate n random matrices again, solve the system, compute n sets of model logs, compute the misfit, and the whole process is repeated until the petrophysicist thinks that a good solution has been reached. Here is a reminder of how the standard multimineral analysis works for the inversion of fractions. Basically, we use one matrix at a time, and this matrix is modified manually in a trial and error fashion until the petrophysicist finds a good fit between measured and model data. And this fit comes from the inspection of the agreement between the two curves on the screen. On the contrary, when the multimineral analysis is performed with the help of a genetic algorithm, we examine many matrices at the same time. The misfits are computed numerically and not by visual inspection. And the most important part is that the modification of the matrix is performed adaptively using the rules of the genetic algorithm. Also, we're adding an additional loop to the process to allow for the adjustment of the ranges of the different constants. This slide shows how the data fitness changes as we increase the number of generations or iterations. So in blue is what is called the optimal solution, that by design in the genetic algorithm is always equal or better than the fitness of the previous generation. We also show here the average solution for every generation, and at the same time, we show the worst solution. So we have an idea of the different ranges of fitness that we're having in every generation. After the final iteration, the algorithm produces two outputs. Output number one are the estimated fractions of constituents and well logs, and output number two are the estimated constants. So here is output number one. The model logs are indicated here in blue and are compared also with the measured log. Typically, with this kind of algorithm, we tend to see a very good match between measured logs and model logs. In this particular example, the interval of interest was separated in three different parts, and each of the parts, each of the sub-intervals was modeled using a different model. In model number two, the middle interval, we generated a new artificial rock that we call matrix. And this matrix is basically a combination of quartz and dolomite. The reason why we did that was to be able to estimate the kerogen present in that rock with the amount of logs that we were provided. On the left, we see the composition of the different minerals for the different intervals, which is also an output of the algorithm. Output number two are the matrices of constants. We start with what we call the initial matrices, which are the first guess of the petrophysicist regarding the actual values of the constants. And then this is the final matrix or the result of the optimization. These two matrices can be also compared with one another to see which parameters change, which parameters remain the same. And we could take this matrix into other programs, let's say Excel, to examine in more detail the importance of the different components and how they affect the fitting of the different logs.
The outputs of the algorithm can be analyzed in different ways. Here is a plot of the range of tested constants versus generations. The generation number is in the horizontal axis. The range of tested values is in the vertical axis. And each of the red bars in this plot indicates the range of tested values for every generation. In blue is indicated what was considered to be the optimal solution for that generation, and in green is the initial value or the initial guess from the petrophysicist for that particular constant. We can examine the range of tested constants versus iterations in real time and use this information to make decisions about how to change the ranges for future runs of the algorithm.
The way how we would do that is examining after the final iteration where is the optimal solution relative to the initial ranges of the different parameters. So in this particular example, for the gamma ray of kerogen, shale, and matrix that vary between a minimum and a maximum value, we see that in these three cases, the optimal solution tend to go very close to the upper limit or to the maximum for each of the ranges. So this suggests that for other iterations of the process, this initial range of values should be increased. Another output of the algorithm is a cross plot of the fitness versus the parameter for each individual that was tested during the optimization. In these plots, every dot represents an individual. When the values that are tested for every parameter cluster around a certain point for the best fitness, we say that the algorithm is tending towards a unique solution, like in the example that is presented here with the cost plot of fitness versus U of the metric. On the contrary, when the best fitness can be achieved or can be reached with many individuals or with many different individuals, we see that we are in the presence of a non-unique solution for that range of values. Here are the results explained in the previous slide, but now in a matrix form for all minerals and fluids and all logs. And we use this kind of display to get an idea of the uniqueness or non-uniqueness of the constants involved in the optimization. Now that we have discussed the details of the implementation of multimineral analysis using genetic algorithm, let's discuss some possible applications. Besides the usual applications of multimineral analysis to estimate the composition of the rocks, the use of the genetic algorithm to estimate the constants of the minerals and fractions can be used for other purposes. In this presentation, we will give an example of how to use the algorithm to identify kerogen grain density trends. We're going to correlate that with thermal maturity. Also, we're going to show an example of independent quantification of variable water resistivity trends. Another ways that we can use this algorithm for is to identify bypass pay, create effective hydrocarbon pore volume ranges, and perform uncertainty analysis for petrophysics constraints in reservoir modeling. The example that we will show comes from the Marcellus unconventional play. And here we show structural cross-section across different wells in the northern part of Pennsylvania when the border with New York. In this analysis, we used 7 wells, but in the cross-section, we're showing only 5. The vertical depth difference between the target across the different wells is approximately 2,000 meters. When we look at the wells in a stratigraphic cross-section that has been flattened for the lower Marcellus, we see the results of the algorithm in terms of the composition and the fluids. We're going to talk about this in more detail later, but I wanted to show another piece of information that we also had for this particular example, which was the kerogen maturity estimated from vitrinite reflectors. As you can see here, the kerogen maturity increases with the depth of the target interval. And we're going to be analyzing these results in more detail later.
Here is the input coefficient matrix that we're going to use for the optimization. In this particular case, we're going to solve for 7 minerals using 6 logs plus the unity constraint. And each coefficient is defined by 3 parameters: the minimum range, the maximum range, and the initial guess of the coefficient for the first iteration.
Here is output number 1 of the optimization that consists of model logs and the composition or the fractions of the different minerals present in the rock. We can see here the difference between measured logs and model logs. Overall, the agreement is very good. In some places, as we can see, there are still some differences, but we believe we have a model that is predicting the measured logs very, very, very closely. When we plot the results for the different wells in cross-section, this is what we obtain. Again, there are 4 tracks for each well. First track will be the gamma ray. Second track will be a comparison between DT and RT logs. The third track is the composition that came from the nonlinear optimization, and the last track are simply the fluids. As you can see, the kerogen composition, kerogen here is indicated in black, changes vertically. This kerogen composition was calibrated with core measurements that we are not showing here. Also, the porosity estimates from the algorithm were calibrated with porosity from core that we are not showing. The deepest well in the section contained more water, and this well was found to be non-productive in this area. Then we analyzed the difference between input versus output coefficient metrics. So here is the initial matrix of constants that we use for the optimization. And here is important to emphasize that the same initial matrix was used for the optimization of the 7 wells. Then the algorithm was run using exactly the same parameters, exactly the same initial matrix for all wells. And we obtained, after the optimization ended, versions of this final metric for the different wells. Once we did that, we started analyzing the difference in 2 parameters in particular. One, the conductivity of water. We analyzed how it changed from the initial to the final metrics. And the other parameter that we examined in detail was the density of the kerogen, how that density changed from the initial metrics to the final metric. And here is the result of the analysis of the variations of the constants for the different wells. First, we start by plotting the thermal maturity estimated from vitrinite reflectance versus depth, and we see that there is a clear increase of maturity versus depth. Second, what came from the algorithm, which is the modeled water resistivity, was plotted also against true vertical depth. And what we see is that after a certain depth, there is a marked decrease in water resistivity. And the way we interpret this is that this might have to do with conversion of kerogen into pseudographite, which is very conductive. Not all this is caused by water, and there is published evidence about this observation in the literature. Finally, we plot the results of the modeled kerogen grain density versus thermal maturity. And what we see is that there is a clear correlation between thermal maturity and kerogen grain density. And we can even see two trends for this correlation. One above 2.5 thermal maturity RO, and a different trend below this number.
Finally, to summarize, what we have seen is that the genetic algorithm-based multimineral analysis allows the estimation of the mineral coefficients or endpoints in areas where the coefficients are uncertain. It automates the time-consuming manual trial and error process of estimating mineral constants in the conventional way multimineral analysis is usually applied. It also generates a multimineral good enough solution that predicts the input logs and output diffractions of fluids and minerals present in the rock. Since the process is much faster, it allows the petrophysicist to explore different types of assumptions and estimate, for instance, spatial variations in important parameters such as water resistivity, kerogen maturity, and clay composition. And finally, in all this analysis, the petrophysicist's judgment and calibration with independent data are fundamental to ensure that the solutions are plausible.